When a single data scientist begins testing a new AI prototype, the environment is deceptively simple. A locally hosted notebook runs a few discrete Python scripts, feeding raw prompts into an external model provider. But pushing that prototype into a production environment breaks the illusion. Code that functioned perfectly in a sandbox degrades rapidly when it relies on hard-coded API keys, manual network configurations, and bespoke deployment scripts that no one else in the company knows how to maintain. The core organizational failure occurs when AI engineers operate as shadow IT. Without shared standards, every single project team is forced to reinvent basic operational infrastructure, from authentication to data pipelines, before they can deploy their domain logic. At scale, AI workloads function as distributed systems. Success depends on coordinating autonomous agents, external tool execution, real-time event streams, vector memories, and human-in-the-loop approval workflows. Attempting to scale these distributed systems without a standardized foundational platform generates exponential operational debt. The engineering hours spent patching together custom infrastructure completely erase the anticipated business value of the AI itself. The architectural solution to this operational debt is an internal developer platform, or IDP. An IDP functions as an AI operating system, replacing artisanal scripts with industrialized infrastructure. We map OS concepts directly. The platform's control plane is the kernel. LLM agents are individual processes, and external tool integrations operate as device drivers. This division of labor creates a clear boundary. It provides the shared machinery required to run complex systems, allowing domain teams to focus exclusively on their specific business logic and intelligence capabilities. To understand how this executes in practice, we have to construct this AI operating system layer by layer, starting from the foundational compute infrastructure all the way up to the user interface. Establishing this hidden operational infrastructure, the dark matter of AI, creates the technical substrate required to make enterprise deployments secure and reliable by default. The foundation begins with the runtime layer. Multi-cloud Kubernetes clusters handle agent workloads across regions, but compute requires state. The data plane isolates stores based on performance, Redis for rapid caching, and vector databases snap in for long-term memory and semantic search. Beneath that fast retrieval layer, data lakehouses using Apache Iceberg securely store the massive offline datasets needed for evaluations, feature history, and model training. A robust multi-cloud runtime is useless if it lacks a heavily optimized multi-tier data plane to feed context to the agents. Connecting the compute containers to the data silos requires an internal network fabric designed specifically for zero-trust security. This hierarchical diagram maps the network structure. AI traffic must traverse multiple trust zones. The global edge gateway absorbs external traffic and validates identity. The domain gateway enforces fine-grained authorization and quotas. Finally, the service mesh ingress manages encryption and internal service identity. This multi-gateway approach effectively air-gaps sensitive internal processing services from the unpredictability of external internet traffic. Without these stripped, hierarchical trust zones, a single compromised prompt could bypass authorization and pivot directly into unrestricted internal network access. Inside that secure perimeter lies the LLM gateway. This is a mandatory control point. No agent is permitted to call an external model API directly. Every request must funnel through this central node. Consolidating model access governs execution. The gateway tracks cost metrics, enforces PII redaction rules, and triggers strict safety filters. Look at this configuration block. This routing policy demonstrates how the gateway manages model failovers. If the primary Gemini model degrades, traffic instantly routes to OpenAI or Anthropic fallbacks. It also enforces an 8,000 millisecond latency threshold and a 35-cent budget cap. The gateway is also where the platform captures semantic telemetry. It logs critical operational metrics like token counts, specific tool selections, and final response latency.
However, there is a strict security constraint.
The gateway must extract analytical metadata without capturing sensitive chain-of-thought logic or storing raw private prompt bodies. By enforcing these rules, the LLM gateway transforms unpredictable, high-variance third-party models into governed, measurable internal services. There is a common misconception that distributed AI agents should communicate by sending commands through synchronous REST APIs. Synchronous dependency chains inevitably shatter mid-execution. When a workflow requires a database lookup, an API call, and multiple sequential model generation steps, the accumulated latency creates timeouts that crash the entire process. To solve this, the architecture relies on Apache Kafka. It acts as the central, durable event bus, providing asynchronous inter-process communication between decoupled agents. Kafka records every single agent step, tool invocation, and memory retrieval as a durable, replayable business fact, packaging the data inside a standardized event envelope. Systems writing to databases must use the outbox pattern. This requires writing the business logic and the event record in the exact same transaction, preventing a split-brain state where a database updates but the downstream Kafka event fails to publish. An event-driven architecture ensures that autonomous agents can hit rate limits, fail entirely, pause, and safely resume their workflows later without corrupting the downstream data. Managing all these underlying network, data, and compute layers requires a centralized brain. This is the platform control plane, the AI operating system's kernel. Engineers interact with this kernel through Backstage, a primary developer portal where product intent is defined and translated into automated system execution. This manifest shows a declarative request for a vector store. Instead of manually provisioning servers, the developer simply specifies their requirements: the QDrent engine, a 1536 vector dimension count, and their specific tenant assignment. The control plane reads this declarative request and automatically generates the precise Kubernetes manifests, Terraform modules, and observability hooks required to build it perfectly to standard. Translating intent into code eliminates manual IT ticketing queues, allowing teams to provision self-serve infrastructure while strictly adhering to enterprise security baselines. This reference architecture illustrates the complete platform, held together by a strict operational boundary governed by domain-driven design. The platform team owns the foundation. They maintain the Kubernetes substrate, the GitOps delivery pipelines, the service mesh networking, and global security policies. The domain teams own the intelligence. They are strictly responsible for maintaining their prompt templates, agent role definitions, business workflows, and customized evaluation criteria. Enforcing this separation of concerns ensures that the centralized platform team never becomes a manual bottleneck, slowing down product feature delivery. Simultaneously, it prevents domain teams from bypassing security reviews and building fragile, non-compliant shadow infrastructure in dark corners of the corporate network. The true value of the AIOS becomes obvious during a new deployment. An engineer opens the developer portal and selects a golden path template to initiate a completely new retrieval augmented generation pipeline. The request triggers an immediate cascade of automation. Continuous integration workflows validate the code, policy engines verify security compliance, and Argo CD deploys the fully verified manifests directly to the cluster. Alongside the deployment, the platform instantaneously generates the required observability dashboards, configures log aggregation, and deploys telemetry stubs to monitor the new pipeline's health. The developer skips the complex YAML archaeology phase entirely. They immediately begin writing valuable domain logic, confident that the infrastructure underneath them is secure. The Omni-Agentic Platform IDP solves the organizational failure of artisanal prototyping. By standardizing the complex operational machinery, it guarantees that enterprise AI systems are industrialized and production-ready by default.